Today we're going to talk about lesson 521. We're going to talk about sequences. In the bouncing ball activity from earlier lessons, you used multiple representations, a table, an equation, and a graph, to represent a discrete situation involving a bouncing ball. Today, you will learn about a new way to represent a discrete pattern called a sequence. A sequence is always discrete, not continuous, meaning that when you graph it and you plot your points, you will not connect the points with a continuous line. We're going to start with this sequence today. We have 2, 6, 18, 24, and it continues. In order to find more terms in the sequence, we need to find a pattern. So if you look at the 2 and the 6, you could add 4, but if you add 4 to 6, you're not going to get 18. So we would have to find some type of pattern that would get us from one term to the next. So if you look carefully, you'll see that if you want to get from 2 to 6, you could multiply by 3. And if you go from 6 to 18, you could also multiply by 3. And you want to find that constant that will take you from one term to the next. And that constant has a name. That is called a sequence generator. And that sequence generator in this case is I'm going to multiply by 3. And I can use that sequence generator to find a couple more terms in the sequence. So if I take 24 and I multiply it by 3, then I would get 162. And if I multiply that by 3, I would get 486. Now, we want to find the sequence using the same sequence generator. We want to find the next 4 terms if the sequence starts with 5. So if I start with 5, and I want to find the next 4 terms, and it said to use the same sequence generator, which in this case is multiplying by 3. So 5 times 3 would be 15. 15 times 3 would be 45. 45 times 3 would be 135. And 135 times 3 would be 405. So you can see how to use your sequence generator to find more terms in your sequence. In the next part, we are going to look at some sequences. We're going to try to come up with what the sequence generator is. We are going to record the next 3 terms in the sequence. We're going to record each sequence in a table, and then we will find the graph of the sequence, and we'll be able to see what kind of a sequence it is. Just remember that every time you graph a sequence, you will not connect the points with a line. Okay, here's our first sequence. We have -4, -1, 2, and 5. And we want to look at that and see, okay, how is it going from one term to the next? So the easiest place to look is the 2 positives right here. If we go from 2 to 5, what are we doing? Well, it looks like we're adding 3. Well, let's check it over here. If I have -1 plus 3, I get 2. And if I have -4 plus 3, then I get -1. So it looks like my sequence generator, and I'm going to abbreviate, is I'm adding 3 each time. So here, my next term, 5 plus 3 would be 8. 8 plus 3 would be 11. And 11 plus 3 would be 14. Now, once you have your sequence filled out, you're going to come down here and you're going to look at the XY chart. Well, in this case, when we do a sequence, we don't use X and Y. We use N to represent the term number, and we use T of N to represent the terms. So, one thing that you guys need to remember is that a sequence will always start with the first term. It won't ever have 0 as N at the very beginning. It'll have 1. So if n equals 1, my first term is -4. My second term is -1. My third term is 2. My fourth term is 5. My fifth term is 8. My sixth term is 11. And my seventh term is 14. And again, in your chart, you can see that these go up by 1, n goes up by 1, and these go up by adding 3 each time. Once you have your XY chart, or in this case your n t of n chart, we can graph it. So on your graph, you're going to plot the points. You have 1, -4, so you go over 1, down 4. Now your graph may have been cut off a little bit, so just estimate the best you can. All the points may not fit on the graph when you graph today. All right, go over 2, down 1, and go over 3, up 2, go over 4, up 5, go over 5, up 8, go over 6, up 11, and go over 7, up 14. Now I may go a little bit faster than you guys, so you can always pause the video to catch up if you need to. Alright, so look at that graph. What kind of a sequence did we just graph? It looks like it makes a straight line. So we're going to say that we just discovered that this is a linear sequence. And the reason why it's a linear sequence is because my sequence generator, I'm adding 3 each time. It grows by 3. Now, we could actually come up with the equation of the sequence. And again, since we have n and t of n, we're not going to use x and y. We're going to use t of n as y, and we're going to use n as x. So, to write an equation of a linear line, we are going to find your slope and your y-intercept. Well, my slope, it's increasing by 3, and my y-intercept I have to find. So if I go up to 0, even though my sequence doesn't have a 0 term, I can still find it to find my starting point. So if I add 3 going this way, I'm going to subtract 3. I'm going to get -7 right here. So my b is -7. So when I write my equation, even though I'm using y equals mx plus b, I'm actually using t of n for y. My slope is 3, my x is really n, and my b is -7. So there is the equation of the sequence that I graphed. All right, that's the first type that we're going to talk about today, are linear sequences. Let's move on to the next one. Okay, here we have another sequence. So you're going to look at that sequence and see, okay, what is happening to get from one point to the next, or one term to the next? To go from 3 to 6, I could add 3, but when I go from 6 to 12, I'm adding a lot more than 3. So I'm not adding the same thing every time. Instead, what's another way I can go from 3 to 6? Well, I could multiply by 2. And if I multiply 6 times 2, I get 12. And if I multiply 1.5 times 2, I get 3. So it looks like my sequence generator is multiplying by 2. So 12 times 2 would be 24. 24 times 2 would be 48. And 48 times 2 would be 96. So there's my completed sequence. When I fill in my XY chart, again, in this case, it's n/t of n chart. My first term is 1.5. My second term is 3. My third term is 6. My fourth term is 12. My fifth term is 24. My sixth term is 48. And my seventh term is 96. Now I'm going to graph that on my graph and see what kind. This is a little bit different. I'm not adding 3, right? Like I was in the other one. And when I added something, I got a linear sequence. Well, in this case, I'm multiplying by 2, so I may get a different type of graph. Let's see what it is. If I go over 1, up 1.5, I'm going to be about right there. And then I go over 2, up 3. I go over 3, up 6. Over 4, up 12. Over 5, up 24. Over 6, up 48. Now I'm going to be off my graph, so I know it's going to be up here somewhere. And of course I'm not going to be able to graph the 796, so I'm not going to worry about that. Well, if you look at that graph, it's definitely not linear. And you'll notice that it starts increasing really slow, and then it starts increasing really fast. Because remember, we're multiplying by 2, so we're doubling each time, so it grows really fast. So can you guys remember what type of graph we get when it starts increasing slowly, but then starts going really fast? Well, it's not linear. We would say this is exponential. This is an exponential sequence. And it grows by multiplying by 2. So if we wanted to write an equation for this, since it's exponential, we learned a formula for that also. We know that we need the starting point and we need the multiplier. In this case, my multiplier is 2. So my starting point, again, I'm going to go backwards to 0. Here I'm multiplying by 2 going down, so when I go backwards I'm going to take 1.5 and I'm going to divide it by 2. Do the opposite. So I get 0.75 as my starting point. So when I write the equation, I'm going to have t of n is the starting point, which is 0.75, times my multiplier, which is 2, raised to the nth power. So for every n, as n increases, I'm going to multiply by another 2. And there is my equation of this sequence. All right, next one. Here we have a new sequence. Now, when you look at this one, when you go from 0 to 1, you're adding 1. And you go from 1 to 4, you're adding 3. And you go from 4 to 9, you're adding 5. So we are not adding the same constant every time. So this must not be a linear sequence. Well, and if I try multiplication, if I multiply 0 times something, I'm not going to be able to get 1. So I'm not multiplying by the same thing every time to go from one to the next. So let's see what's happening. If we can find a pattern, we might be able to figure out what the next 3 terms are. So that also tells me one thing. If I'm not adding something, then it's not linear. If I'm not multiplying by something, then it's probably not exponential either. So this is going to be a little bit different. Let's see what we're going to get. We're going to add 1 here. We're going to add 3 here. And we're going to add 5 here. Well, we're not adding the same thing every time, but you can kind of see a pattern. What would you guess we would add to 9 to get the next term? Notice how we're increasing by odd numbers. The next odd number would be 7. So 9 plus 7 is 16. 16 plus 7 is 25. And 25 plus, sorry, I got ahead of myself. That was adding 9, and this is adding 11. Adding 11 to 25 would be 36. So I'm saying plus 1, plus 3, plus 5, plus 7, plus 9, plus 11. And there's another way to do this. If you guys look, what are special about all of these numbers? Well, 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. And 6 times 6 is 36. These are all perfect squares. So if you would have noticed that before we started, we wouldn't even had to do this part where we're adding something every time. We could have just said, oh, this is a list of the perfect squares. So my first term is 0. My second term is 1. My third term is 4. My fourth term is 9. My fifth term is 16. My sixth term is 25. My seventh term is 36. Well, if this isn't going to be linear and it's not going to be exponential, I wonder what it's going to be. Let's graph it and see. If I go over 1 up 0, I'm going to get a point right there. Over 2 up 1. Over 3 up 4. Over 5. Over 4 up 9. Over 5 up 16. Over 6 up 25. And over 7 up 36. Now, it kind of looks like it could be exponential, but since I'm not multiplying by the same thing every time, I'm adding odd numbers every time. That's something different. This is actually what we would call other. And I will tell you, just for your information, that if we graphed negative numbers, we would actually get a parabola. This is half of a parabola. So this is actually, in this case, this is a quadratic sequence. Now we're not going to talk about quadratic sequences a lot at this point, so we're not going to worry about finding the equation of this one. I just wanted you to see that if it's not adding the same thing every time, or it's not multiplying by the same thing every time, it's going to be other. It's going to be some other type of sequence besides linear or exponential. Okay, next one. Let's look at this one and see. This one's a little different because notice the numbers are getting smaller. What is happening each time as I go from 9 to 7, 7 to 5, 5 to 3? Well, looks like I'm subtracting 2. I'm subtracting 2. I'm subtracting 2. So my sequence generator is subtracting 2. Or, what is another way I can say I'm subtracting 2? Well, isn't subtracting 2 the same thing as adding a negative 2? So I am adding the same number every time. And so if I'm adding the same number every time, it happens to be a negative number, what kind of a sequence do I have? Well, we'll see in just a second. When I subtract 2 again, I'm going to get 1. 1 minus 2 is negative 1. And negative 1 minus 2 is negative 3. So I completed my sequence. I'm going to write it in my n t of n chart. I have my first term is 9. My second term is 7. My third term is 5. My fourth term is 3. My fifth term is 1. My sixth term is negative 1. And my seventh term is negative 3. I am decreasing by 2 each time. So when I plot it, I go over 1 up 9. I go over 2 up 7. I go over 3 up 5. Over 4 up 3. Over 5 up 1. and over 6 down 1, and over 7 down 3. You can see that this is a linear sequence. And that is because it grows by adding a -2 or subtracting 2. All right, so we want to find our B and our M. Well, our M, we're subtracting 2 each time. And our B, our starting point, we would go up to 0. And since we're subtracting 2 going down, if we add 2 going backwards, we're going to get 11. So B equals 11. So my equation would be T of n is equal to -2n plus 11. There is the equation of this sequence. It's going down, it has a negative slope. And it makes sense because it's going down in my graph also. So this is also a linear sequence. When you add or subtract something, a constant, then you have a linear sequence. Okay, number 5. This is the last one. We are going down again, but if we find the difference between 48 and 24, we're going down by 24. Here we're going down by, between 24 and 12, we're going down by 12. So we're not subtracting the same thing every time. So we're going to look at dividing. If I divide by 2, I get 24. And 24 divided by 2 is 12. And 12 divided by 2 is 6. 6 divided by 2 is 3. And 3 divided by 2 is 3 over 2, or we could say 1.5 if you divide it on your calculator. So my sequence generator is dividing by 2. Now, is there another way we could say that? Because if we could turn this into multiplication instead of division, then we would know that we would have an exponential sequence. Dividing by 2 is the same thing as multiplying by its reciprocal, multiplying by 1/2. So you can think of it as dividing by 2, but you can also think of it as multiplying by 1/2. All right, so our first term is 48. Our second term is 24. Our third term is 12. Our fourth term is 6. Our fifth term is 3. Our sixth term is 1.5. All right, so in this case, we're dividing by 2 or we're multiplying by 1/2. Let's see what the graph looks like. I'm going to go over 1 up 48. Now I can't get it on there, so don't worry about it. Go over 2 up 24. And then we have over 3 up 12. Over 4 up 6. Over 5 up 3. And over 6 up 1.5. So you can see that if it was at 48, we would be way off the graph up at the top, but it's decreasing, and it's eventually getting less and less steep. So it's an exponential sequence because of the fact that it grows by dividing by 2 or multiplying by 1/2. Since it's exponential, we can come up with the equation. We have to find 0. If I am dividing by 2 this way, going down, then I must be multiplying by 2 going up. So this is going to be 96. So my starting point is 96. So I say T of n is equal to 96. What am I doing to it each time? I am multiplying by 1/2, and I'm going to multiply it by several times as I go down through the sequence. So there's my n. Okay, now we're going to summarize. What have we learned today? We learned that a linear sequence you are going to add a constant to get to the next term. We can also say we could subtract a constant. Now, this has a special name. The linear sequence like this, we actually would call an arithmetic sequence. So in your homework, they're going to have, what type of sequence is this? And you're going to say, instead of linear, you're going to say arithmetic. Okay. The other type of sequence we learned today was an exponential. And this is when you're multiplying by a constant. Or you're dividing. This has a special name too. We call this a geometric sequence. And then we had a third type. The third type, we called it other, and an example would be quadratic. We had a quadratic sequence. And the quadratic sequence does not grow by a constant. And we don't have a special name for a quadratic sequence or the other sequence. So all you have to worry about are the arithmetic and the geometric sequence. Look to see, is it adding or subtracting each time? It's arithmetic. If it's multiplying or dividing each time, it's geometric. And that is all for today.